Hello, everyone. Last day we were looking at, or in the last lesson, I should say, we're online now. We're looking at the lesson on Hooke's Law. So studying both the horizontal and vertical motion of springs and how springs can behave as a simple harmonic oscillator or undergo simple harmonic motion. It's where they go back and forth in that periodic or sinusoidal-like motion. Now is where we're going to tie springs back into the previous unit we did, and we're going to look at the elastic potential energy for a spring. Okay, so springs, of course, when you stretch or compress them, have the ability to do work. If you push a spring down and then let it go, it'll spring back. If you had put something in its way, it could spring back and pushing it, thereby transferring its energy to another object. So springs do have potential energy. They have a type of stored energy, and they have the ability to do work on another object. And we call this stored potential energy of a spring or an elastic potential energy. Okay, so what we're going to do is we're going to derive the equation for elastic potential energy first by examining the force on a spring. Okay, so work first is done to stretch or compress a spring. So we apply a force over a distance. If you remember, that's our equation for work, force times distance. So we apply a force over some distance to either compress or stretch a spring. So if we were to graph that force, let's say we have a spring and we stretch it some distance x. Okay, and at x, it requires a maximum force of here at the top of this graph to stretch it some distance x. Okay, so that's our F max. Now, if you've ever played with an elastic or a spring or something, or as you saw in the previous lesson when we looked at the oscillating spring and how the acceleration changes, force is not constant when you stretch or compress a string. In fact, the closer it is to its equilibrium position, the less force you have to apply. The farther you get away, the more force you have to apply. So when dealing with energy, we're actually looking at the average force, okay, which is going to be half of the maximum force. So we're going to look at a couple of different ways we can think about calculating this. But first, if you remember, the change in energy is equal to the work done in a system. So this is how much work you input into a system to change that system's energy. Work is equal to a force times a change in distance. Okay, now if we look on our graph, we have force here on our y-axis and we have distance on our x-axis. Okay, so we can think about this in two different ways. You can think about the fact we're using the average force, which is half of the max, or the area under the curve. So here we have a triangular shape. Okay, if we calculate this area, remember area of a triangle is 1/2 base times height. Well, what is our base but our distance, and our height is our force? So we get 1/2 force times our change in distance, which is very similar to our energy equation here. Now, if force was constant, most of the time in our previous, so this equation to the right here that we've used previously, we assume we have a constant force. Force is not constant anymore, so that's why we have to have this term of 1/2, because we're looking at the average force, not the maximum force that is applied. Okay, so this equation then becomes delta E equals 1/2 force times the change in distance. Now we're dealing with a spring, so we're specifically looking at the spring force, and remember a change in distance in a spring, we give the symbol x. So if we substitute our force here, spring force is equal to kx, okay, and then distance is also equal to x, so we end up with the equation delta E is equal to 1/2 k, which is our spring constant, times the distance you move it squared, or 1/2 kx squared. So this is our potential or our spring energy. Okay, at the equilibrium position, which would be down here at the bottom of the graph, it crosses through zero. That's because the energy at equilibrium is zero. There is no potential energy. That's the spring's resting place. Okay, so when we deal with energy, we also have to deal with the conservation of energy. So imagine for a second again, we have a spring. This is its equilibrium position here. Okay, there's no energy when it's at that position. So we apply a force, we pull that spring downward, okay, using a force, we give it potential energy. What happens when we let it go, so at the bottom here it has potential, when we let that go and it starts moving back up toward its equilibrium position, its potential energy is converted into kinetic energy. Okay, so at the bottom, it has all potential energy, and at the equilibrium position, we already discussed there's no potential at the equilibrium, but so at the equilibrium it'll have all kinetic energy. And as in our previous units, okay, our total energy is equal to kinetic energy plus our potential energy. And we can make some substitutions here. Kinetic energy is the same as before. It's 1/2 mv squared. Okay, and our potential energy, now we're looking at spring potential, so it's 1/2 kx squared. So you can find the potential energy of anywhere in a spring system by looking at this total energy equation. Now something important to note, at the bottom here, so when we're down a distance x, which we can call the amplitude, okay, because that's the farthest we are away, so it's our amplitude of our spring, all of the energy here is potential energy. So it's all potential. So that means our total energy at this point at the bottom is equal to 1/2 times the amplitude, 1/2 k spring constant times the amplitude squared. Okay, so that's when we're at the very maximum distance away from equilibrium that we're going. At the center point, at the equilibrium, it's all kinetic energy. So at this point, our total energy is equal to 1/2 mv, and since it's all kinetic energy at this point, so there's all energy has been transferred to motion, this is going to be our maximum velocity at this point, and it's v squared. So 1/2 mv squared when we're at equilibrium, and 1/2 ka squared when we're at the amplitude. At any other point within this system, we use our total energy equation, which is the addition of the two energies together. Now, all of this, too, is ignoring the fact that there would be friction or potentially some other forces on the spring, but we are ignoring those and assuming that energy is completely conserved within the system. Okay, so let's have a look at an example. So a spring with a spring constant of 125 newtons per meter is attached to a 245 gram mass. So it's hanging, it's just at equilibrium. The mass is then pulled an additional distance of 2.5 centimeters from equilibrium and released. What is the total energy of this system, and what is the maximum speed of the mass? So we'll start with part A. So again, we have our system. Let's assume it's a vertical spring. Okay, so a spring is hanging down. It's then pulled an additional 2.5 centimeters. So that is our additional x that it's pulled, which is also our amplitude. So that's how far it's pulled down. And then it's let go. So we have our initial equilibrium point here. It's pulled down to its new equilibrium point. I should shift that x down since I'm measuring from the center of the block, not the top. It doesn't actually matter which point you choose to measure from as long as you're consistent in both. So what we know about this system is our spring constant is 125 newtons per meter. Okay, our mass is 0.245 kilograms. And our amplitude, so the farthest distance we pull it down, we always want to switch things into meters, so 0.025 meters. And from this we can calculate our total energy of the system. Okay, so energy total is equal to, since we have our amplitude, we know our maximum is 1/2 Ka squared, which will be 1/2 125 times 0.025 squared, which equals 0.039 joules. Okay, so for part B, it's asking what is the maximum speed of the mass? Well, maximum speed takes place at the equilibrium point, so back when it's here at our 0 point. Okay, so at that point we have no potential energy, so all of the energy goes into kinetic. So we can set up our equation. Total energy is equal to 1/2 mv max squared. Okay, we know our total energy now. 0.039 is 1/2 times 0.245 kilograms times v max squared, giving us a maximum velocity after rearranging and solving of 0.56 meters per second. Okay, so let's take a look at one final practice problem. Again, feel free to pause and try this one first before I go through it, so you get a chance to see what solving it's like. So a block of mass 0.5 kilograms is placed on a level frictionless surface. So we're dealing with a horizontal spring in this case, but no friction. Some of your homework problems will have friction in it. It's placed in contact with a spring bumper that has a spring constant of 100 newtons per meter and has been compressed by an amount of 0.3 meters. The spring, whose other end is fixed, is then released. So what's happening here, I'll draw it down at the bottom, is we have a spring attached. Imagine the spring is just attached to a wall. Okay, and there's a box on the end of the spring at rest on a frictionless surface. That box is then compressed. So we're pushing that box back to the amplitude, which is 0.3 meters. So I know I'm writing on top of words here, but 0.03 meters. So that's how much it's being compressed by. Then we're letting it go. Okay, when we let it go, it's not going back to 0, which is our initial position here. It's heading back, and we're asked to find the speed when it's 0.10 meters away from its initial starting point. So it still has a bit of compression, which means there's still a little bit of potential energy there. Okay, so to solve this one, the one thing we know is that the energy is conserved within a spring system. Okay, so first let me just write down my variables here. So we had a 1/2 kilogram mass. The amplitude of our system, so the farthest it was stretched, was 0.3 meters. The position we're trying to examine, the final position, is 0.1 meters from the equilibrium point. We had our K is 100 newtons per meter. And we're looking for the velocity. So in this case, we know that the energy is conserved, so we can use our conservation of energy equation. Initial energy is equal to final energy. In the initial energy, all we have, since we're at the amplitude, is 1/2 Ka squared. It's all potential at the start. And at the end, we have a little bit of both. We have some kinetic energy and some potential. So it'll be 1/2 Kx squared, because we're not at the amplitude anymore, plus 1/2 mv squared for our potential energy, or sorry, for our kinetic energy. The 1/2 terms here will cancel out on either side. Don't have to worry about them. So we get 100 times 0.3 squared is equal to 100 times 0.10 squared plus 0.50 times our velocity squared. Okay, after simplifying and rearranging, you'll find that the velocity is equal to 4.0 meters per second. as the final answer. Okay, and that actually brings us pretty much to the end of what we're going to learn about springs. So for this section, do the homework problems in problem set 2.4.2. Give all of them a try. Um, we're finished looking at springs, but we're not finished looking at simple harmonic motion. So in the next video, we're going to look into a little bit into pendulums or simple pendulums. All right, and with that, have a good night and good luck on your homework.